2016. So focused on bringing automation in business processes, using ML and deep learning in enterprise applications, security, privacy, blockchain, industrial IoT. So next week we have the CTO of GE Digital, Haral Kodesh, speaking on industrial IoT. And then a lot of interest. Look out in the later part of the year for events around computer vision, AR, VR, and then UAVs. Some of our companies are hiring, so if you're interested, Coinalytics is providing real-time intelligence for blockchain. And the reason that's difficult is blockchain is inherently privacy preserving. So it's not easy to do KYC and AML and these kinds of applications. The second company featured here is Neva. And so Neva is providing business process intelligence so that you can create software robots for business processes. Instead of thousands of people in Philippines and India, now you have a software robot that can automate a lot of the processes. So with that, I'd like to, so if you're tweeting today, please use the hashtag #HiveData. And so with that, I'd like to welcome our hosts from Pivotal to say a few words.
So I just wanted to welcome you all to Pivotal. I'm with Pivotal Labs. I'm a software engineer. My name is Shane. And we're glad to host the event here. And just want to say some quick words about what Labs is before turning the field over. Labs is a software consultancy firm. We focus on agile methods, test driving every piece of code, and pair programming. We help enterprise companies develop software faster and get out the door quicker at a sustainable pace that's good for engineers and works in the long run. We're glad to be here tonight, so I'll keep it real short. But if you have any questions about Labs, I'll be here afterwards, so please talk to me. Thanks.
So I would like just to welcome all our speakers here on the stage. So they will be just switching seats. So Weil, would you like?
We are excited to have Dhruva Borthakur from Facebook here. We have been following the evolution of RocksDB since the time when they started working on it at Facebook. I'm happy to see some old guard folks from the database world, like C. Mohan here also. And so the way this will work is we'll have the first portion will be Dhruva speaking on and kind of running a discussion on the roadmap and vision for RocksDB. Following that, we'll feature a bunch of use cases. So over Google Hangout, we'll have Sage Weil, I guess that's how you pronounce it, talk about a file system use case, in this case Ceph, and then you'll see some use cases around databases, so in this case MongoDB as well as MySQL. And then our good friends at Rakuten will talk about how they're using RocksDB in a marketing context. With that, I give you Dhruva.
Thank you, Ravi. Hey, good evening, guys. How are you guys doing? So is my voice very jarring? Should I speak softly or can you guys hear me? Okay, cool. So thanks for coming, and thanks to Pivotal and thanks to Ravi for organizing this event. I am here today. When I discussed this with Ravi, I said that, hey, RocksDB is an open source project. So is there any value in collecting opinions and ideas from people, saying that what are the things that are interesting for RocksDB to do, and kind of help shape our roadmap so that we can satisfy requirements from people who are using RocksDB in the real world. So that's the topic of my discussion. And I would like to make this interactive so that you guys can contribute things, and I'll keep a note of these things. And hopefully some of these discussions will shape how RocksDB's roadmap shapes up in the future. So RocksDB is an open source project, so there is no central authority saying that this is how the roadmap should be. So that's why I think it is interesting for us to gather ideas and opinions from the open source development. Make sense? So I have a set of slides, but I think my goal is mostly to collect ideas. So I would probably stall on some slides and just let you express opinions. So how many of you have actually used RocksDB software? So I see. So maybe 5–10% people have actually used RocksDB. I can see hand on the back side there. And then, so I feel that RocksDB is a software that developers use. It's not a system, right? So if you're a developer, you might be developing for some project and you are using RocksDB internally. So because you are a developer, I feel that you actually have the capability or the interest to change RocksDB code so that you can make it better, right? Because it's part of developers helping other developers. Because it's open source, I think it is interesting, or it is important for us to make sure that we can handle a wide set of workloads. So right now, RocksDB handles some workloads very well, but it is possible that there are some workloads that we don't handle very well. For example, most people store like small keys and values inside RocksDB. I haven't heard people store like huge blobs inside RocksDB, for example. I'm not saying people are using, are needing this use case, but I'd like to hear from people to see whether this is something that is interesting. So, how many of you know what RocksDB is? Okay, so I think let me give you a little bit introduction for the first 2–3 minutes about what RocksDB is, because I talked to 1 or 2 persons, and I think I got the idea that there are some people who basically want to learn what is RocksDB and how they can use it, right? So please excuse me if I'm talking like very elementary things, but that'll be very short for us. So it's a key value store. There are many other key value stores in the world. This is yet another one, and there's like a zillion and billion of them. So why is it that you would need to use RocksDB and not something else? So the first point is that it's an embedded key value store. So if you want to embed a piece of software inside your application, then RocksDB is a definite candidate of choice. It's not a key value store like Cassandra or HBase, because those are systems. You cannot embed it into your software, right? So here, the database is part of your software. RocksDB is more like a database engine rather than a database system, right? So that's one big difference in my mind from many other key value stores. And also, what we have done is that we have optimized it for fast storage. What it means is that if your storage system is very fast, for example, memory-based storage systems or some new storage systems which are talking about different kinds of RAM, then I think RocksDB would be a definite candidate for you to evaluate. And also it's optimized for server workloads, so you can probably use it in your Chrome browser, but it's more suitable for applications in the backend where you might have much bigger data sets. Again, the API is very simple, keys and values. Everybody understands this. And then data is sorted by keys. So all the data, when you put it, the system automatically sorts it for you. It's not a global sort, but when you read it, it comes out as if it's a global sort order. The main APIs are put, delete, and merge. So you can put data into the database and you can get or delete data and merge keys or the values for the same key. And for queries, you have iterators and gets. Very similar to many other many other key value stores out there. Any questions so far? Yeah, question? It's not distributed. So if it's not distributed, it also means that there is no failover story, right? Because that means you have to design your own failover. It also means that there is no replication story. So you have to build your own replication stream somehow into this. There are other pieces of software that is built on top of RocksDB to give you a distributed story and replication. And that's what I meant by saying that we have used RocksDB in many other systems which give you these other features. So RocksDB's main focus is performance. So the big picture again, probably I'll spend 1 minute on this one. most people might be aware of like the LSM engine, the log structured merge database. So what happens is that the write request comes in, it goes to the green piece called the active mem table. It's an in-memory data structure. And the writes also go to the persistent log on the right side. So that's how writes happen. And then when the green piece called the active mem table fills up, it switches and there's a new instance of the active mem table. And those read-only mem tables get flushed to disks or storage or disks on the storage. There could be on SSDs or spinning disks. And then there is a compaction going on which reduces the number of files in storage. So the question is the format same on both? The format, meaning the format of the file on the storage and mem table? I see. So the active and read-only mem tables format is same, but there is no reason why it needs to be same. You could do some transformations if you have extra CPU. For example, the mem tables, we support many different types of mem tables, so I will explain that in a second. Any other questions? So yeah, so there are 2 or 3 different modes of operation. Again, the whole point of RocksDB is to make it flexible so that you can use it for different applications. So there is one mode where you can sync, when you can write to the log and sync it to the disk before you reply. There is other one where you can just write it to the OS buffers and not sync. And there's yet another where you don't do any logging. So you have like 3 or 4 levels of logging. So I have been asked many times by people saying that why does Facebook develop RocksDB? Why is it that there is investment from Facebook to develop RocksDB? And there is no one answer for this question. Anybody want to hazard a guess why Facebook develops RocksDB? Sorry? Because it can. Okay, yes. Because it can. Good answer. Weren't happy with the performance of LevelDB, yes. Or for that matter, many other open source databases we have experimented with. Most of the time we try to experiment with open source database. And when we were doing RocksDB, we did quite a bit of evaluation of the other databases to see what fits our needs. Yes, there are zillions. Yes. Yeah, so I think the question is that if there are a zillion other databases, why can't we find one which matches our needs if there are so many of them? So this is one problem with open source software in my mind. There are too many pieces of open source software. And sometimes I spend a lot of time trying to figure out which open source software to use, and because I feel that a lot of infrastructure engineers like myself, we like to open source stuff. And it doesn't need to be great quality to open source. Open source just means other people can read your code, right? So I think I'd like to capture the answer in like 1 or 2 slides. And one answer is that there's a time when we're running, or there's a time when we run, say, MongoDB for some of our databases. This is data which probably is like a year old, so it might not be relevant to the recent version of MongoDB. But when we are putting RocksDB in production, we could see that like a 5 terabyte MongoDB instance was reduced to 285 gig. So Igor actually has a great presentation today on what was done and why this is. MongoDB might have made more changes in the last 1 year, so this is something that is not very recent, but maybe around a year old. Right, Igor? Around a year old data? So this is one reason, for example, right? So most of our investments are based on data that we collect, not just like thinking that, oh, it's just good to have. And then for MySQL, MySQL by default uses the InnoDB storage engine. This is kind of the common default for many deployments. And what we have seen is that the blue line, well, I think you cannot see it very clearly, or maybe you can. So the database size got reduced when you move from InnoDB to RocksDB by around 50%. And saving our production tier by 50% in my mind is a huge deal in this time. Many times you're struggling with like 5 or 10% gain, and here this gives us 50%. And a lot of our production tiers are bottlenecked by the amount of data we can store. So if you can reduce your flash size, petabytes of flash size by half, that's a lot of efficiency you can get. So in short, this is what Seeing talks about today in great detail. What we are going to do. Seeing is here somewhere. Yeah, Seeing is here there. So I think this number is still valid, right, Seeing? Yeah, so this number is still valid, and he's going to give us great information on what we did to get to this number.
This is the only reason you pick, right?
Sorry?
You are doing MySQL here.
Yes.
You are MongoDB on the border.
Yes.
You like it, so you decided to build one just to create that number.
No, we actually like MongoDB a lot. So there's nothing like we like or not like software, right? All software we like. It's just a question about for this workload, what is the production is going. So we have a workload called link bench. Again, these results might not be true for any of your use cases. So you need to figure out yourself or your workload whether this is true or not. Right? So for this, what we have done is that our workload has a benchmark called link bench. It is open source. And we run link bench on our evaluation databases to figure out which database gives us what performance. And these numbers we are getting is from link bench database, and we have put it in kind of trial production mode, and you're also seeing the same results in production too. Yes, right, sure. But my point I think is that some bad ones for somebody might be very good ones for somebody else. So that's why somebody might have developed it, right? Because it works for their use case. There are a lot of open source software that is not flexible in my mind, so it works great for one use case, but it might not work for some other use cases.
What's the gist of
What is the gist of link bench? So the link bench is Facebook's workload in production. So Facebook has this modeling called objects and associations. That's how we represent our Facebook graph. It's kind of a graph database. And link bench is the workload on this graph database. So there's a paper in Sigmod, I think, which talks about the link bench benchmark. Question?
Performance change? This is just size. How about like performance?
Yeah, excellent question. So this is about size, and on the right side is how many bytes were actually written to the storage. So when we did this experiment, I think the latencies were pretty much similar, but we have seen more improvements, and I leave it to Seeing to talk about it in the follow-up talk. So one of the things that I see people constantly keep telling is that, hey, it's easy to use RocksDB, that's why I use it. So this is the other problem or thing with open source software, right? There are some open source software which were very easy to use, so a lot of people used it. So the same thing with RocksDB is that there are some use cases inside Facebook or some other use cases I know of where they just use RocksDB because it's easy to use. And I think it is easy to use because of a couple of reasons. In the original architecture diagram we saw that we have this mem table and we have this transaction log and we have file formats. The whole point about RocksDB is that all of these things are pluggable. So it's basically made for developers. In the sense that if you want to ship RocksDB as part of your storage appliance, for example, right? Or you are creating some new SSD device and you want to have different compaction mechanism. You can plug and play and replace that part with your own. So for example, the Weil, which is the write-ahead log, can be customized. Then the SSD format, the format of the file on the disk, you can pluggable. So we have two formats right now. One format for block-based devices and one format for RAM-based, which is random access. And I'm hoping that other people can build other SSD formats on the disk. Similarly, say example, the mem table format. This is one question that Mohan asked. So mem tables, we have like 3 or 4 formats. For example, if you are loading data, then we have like a vector mem table because nobody's reading. All you need to do is to just write these things fast into memory. And then when you write it to disk, you can sort it and write it to disk. So we have 2 or 3 different mem table plugins because for different workloads, we need different things. So for your use case, as a developer, I think it's very easy for you to customize one of these pieces. And I guess this is one reason why developers should find it friendly to use RocksDB rather than something else. So you don't need to reship RocksDB in your code as long as you can ship only the component that you have changed to gain advantage for yourself. Make sense? So RocksDB again is not a tool. It's a tool but not a solution by itself. So this is why most of the things we have tried to make it pluggable. Pluggable again means that you don't need to reship the whole of RocksDB when you try to package it inside your application. And our hope is that a lot of software developers will embed it into their solution. Now, who are the guys who have embedded RocksDB inside? Yeah.
But that also means that if you want to update that version of RocksDB that's embedded, you have to install a new version of your application.
Yes, I think the RocksDB will be embedded into your system. So when you ship a new version of your system, you could afford to go with the old version of RocksDB, or if you use new features.
I was asking the other way. If you have a better version of RocksDB, but your application hasn't changed, but you want to benefit from the new version, then you have to ship a new version of it.
Correct, yes. Because it is embedded into your application. Absolutely, yes. So you'd have to ship a new version of your application. Absolutely. So a couple of integrations that I wanted to mention. Again, there are many integrations that I have seen, just people posting stuff, but the interesting ones are the very early ones where we work closely with the teams at LinkedIn, Yahoo, Airbnb and Pinterest, because they have deployments on RocksDB now. Is there anybody here from the LinkedIn team now? I don't see anybody. I think Yahoo Sherpa, I've talked to those people, and they were here in the last meetup. And there are presentations by Airbnb and Pinterest on what exactly they use RocksDB for. So if you search for them, you will find how the use cases are. Similarly, it has been ported to Windows by the Microsoft Bing platform. I don't know exactly how much in development it is there because it's proprietary for them. But they have contributed the Windows port of RocksDB back to open source. So we also have Java APIs for RocksDB. And in the RocksDB project, we actually have some external committers to this project, so it's not just Facebook driven. So some of these external people who have contributed code have actually become committers of the RocksDB project. Similarly, Apache Samja, which is basically a message passing software on top of Kafka. That also uses a RocksDB storage engine. Then there is some Bitcoin style servers that people have written. I don't know again what is the production capabilities of the Ripple server, but it's something to look around. Then we'll hear from Sage today about how he's integrating RocksDB in the Ceph file system. He's the next speaker, so he's going to talk about it. And then open channel SSDs. This is an open source software to bring some of the SSD firmware code back into the host subsystem. So there's some integration with RocksDB. Again, I'm talking about integrations. I'm not talking about what has been deployed in production, because what is deployed usually are proprietary to those guys who are doing this integration. Any questions so far?
I heard of RocksDB is RocksDB, right? RocksDB is a C++ implementation of Cassandra. Could you elaborate what kind of different kind of use case for both systems?
Okay, yeah, I think good question. So RocksDB is C++, that is absolutely right. But we also have like a Java API to RocksDB, and also I know some people have made a Go API to RocksDB. As far as the comparison with Cassandra is concerned, Cassandra is a distributed key value store, whereas RocksDB is a single node key value store. One of the biggest differences. But if you embed RocksDB into, say, MongoDB or something else, then it already becomes a distributed key value store. But if you just talk about Cassandra and RocksDB stock, then they're quite different pieces. That's just because one is distributed and one is a single node.
So you gain your performance. So you gain your performance by make it smaller, less powerful,
Great question.
less feature-rich, right? That's
Great question. Yes.
There's no free lunch, basically, Because Cassandra is also very good, to be honest.
Yeah, great question. I think what his question is that why do we gain performance? So let me give you an analogy, right? Suppose you are building a car. Do you think the same people who build the car also builds the car engine? So most of the time there are two different teams who are building the whole car and the car engine. So this is the analogy I give, saying that hey, the things that you need to build for the engine are very different from building the entire car which is usable. So as far as RocksDB is concerned, most of the time we are focused on building the car engine, which means that it has to meet some stringent performance numbers to be able to drive different sets of cars. And then when you're talking about a system like Cassandra or anything else for that matter, you need to build the whole car with the doors, windows, windshield, wipers, and everything else. So that is the whole entire system. So right now, for example, it is possible that because you have a Java API, somebody could potentially take RocksDB and plug it into, say, the HBase region server. I haven't seen anybody do it, but there's been talk about this one. So then you could get the performance, you can make HBase have the same performance of RocksDB, but have the distributed nature that HBase offers.
I have a question.
Yes, one question.
Do you know an instance where MongoDB uses RocksDB as a storage engine?
Yeah, so MongoDB has RocksDB as a storage. So the question is, does MongoDB have RocksDB as a storage engine? Yes. Instead of their own custom built storage engine, yes. So inside of some deployments, we have MongoDB deployed using the RocksDB storage engine. So you can hear more about it from Igor when he presents this one. Yes.
I thought the gentleman asked the question of whether Cassandra and this one are the same, but for the fact that one is distributed to the other.
I see.
Because
So
of formats and so on.
I see. The formats, the disk format and stuff like that is what you're talking about. No, I think the disk formats should be different. Similarly, the disk format of Cassandra and HBase are quite different. Not because of any technical reasons, but more because of historical reasons.
Plus embedded versus non-embedded, that also is.
Yes, absolutely.
There's in your earlier slide in the architecture, you have the open and pluggable embedded architecture. Does that help in any way with the performance? I want to know, like,
Great.
how.
Yeah, okay. So the question is, how does open and pluggable help in the performance, right? So I'll give a very simple example. Suppose you have a use case where you are using RocksDB for some analysis or analytics, right? So you need to load a lot of data first. When you are loading data, there are no queries, right? So when you're loading data, you could have a customized pluggable mem table, which is say just a vectorized mem table. So you don't need to do a sort every time you insert. So you can do bulk load very fast. And then once you are ready to serve data, when you read this file, then you could use a mem table which is a skip list, for example. So that when you're looking at data, when you are querying this data with some small amount of updates, you can get this data very fast. Similarly, for example, compaction, right? So I also mentioned about pluggable compaction. So we have 2 or 3 models of compaction. So there are some compaction strategies which reduce read amplification, and some compactions reduce write amplification. So these are new ways of measuring how your flash device is doing, for example, right? Like in earlier times for disks, we used to be very particular about IOPS per second. But when you're talking about SSDs, IOPS is not the only thing to measure. We also need to measure read, write, and space amplification. So depending on the compaction strategy that you are using, you could customize it to say that, hey, I have a lot of SSDs, so I can have a lot of space amplification, so I don't need to compact very fast. Right? So you can customize your compaction strategies, for example. Does it answer that? I can give you more examples if you're interested. So yeah, I think for SSDs, I think there are certain advantages to using RocksDB inside SSD or make these two things cooperate and coexist. I'd like to hear ideas from SSD vendors, if there are any, on what they're doing. Question?
What's your comment on MySQL's it's called a multiple engine approach. It looks like your approach is similar to MySQL. Pluggable engine, database engine like that. MongoDB also kind of myself. The other question is how does your RocksDB engine try to find a way to solve the impedance mismatch, both with front-end big data ingestion front-end as well as the back-end. You have to have a CPU and IOPS mismatch, matching as well as data ingestion. So impedance matching between front-end and back-end.
So I think, let me hold on to that question for a second, because I think I would like to explain, if I have time, on how we can match CPU and IOPS that we have on the storage device.
Because your engine might be too fast or too slow. Against the incoming data as well as the back-end computation.
Okay, I think I understand. I think your question is more about streaming data, right? So when there is data coming in and then there is some data going out possibly, how do you match impedance? I don't think there is much about streaming inside RocksDB, so you have to handle it in your embedded application. But if anybody wants to contribute anything or have any ideas, let me know. I don't think data, as far as RocksDB is concerned, there is any streaming component inside the database. So SSD vendors, I believe, is something where I think we can help either reduce, say, page grooming or page cleaning efforts that happens inside the SSDs by joining forces with RocksDB. Similarly, for file systems, I think there are many things that a file system can help to make RocksDB better. For example, when you f-sync a file, we want to make sure that only data for that file is f-synced and nothing else, just so that we can finish the f-sync quickly. We can also try to see how we can reduce contention inside the file system on the mutex when we are allocating blocks and doing reads and writes inside the file system. So if there are any file system engineers who want to work, I think that would be great. Come talk to us, the RocksDB team. Also, if you want to say enhance the RocksDB functionality, there is another thing that we have called stackable DB. Just like you might have heard about stackable file systems, right? So similar concept where you can layer functionality on top of RocksDB. We have TTL support, for example, in a stackable DB. Again, this is another way to keep complexity versus flexibility in two different places. So that you can stack these functionality on top of the core RocksDB piece of code. What I've seen is that usually when a piece of infrastructure is there for a few years, maybe 2 or 3 or 4 years, when new developers come, they find it very difficult to quickly innovate because the code becomes complex. So this is one way for us to keep complexity and flexibility in two different APIs and two different layers. Similarly with GeoIndex, we have Redis style operator, but I think that Redis style APIs needs more work. So if somebody is interested, please see the code and talk to us. So as far as the vision of the product is concerned, the first most important thing for us is to make sure that we have good performance. And based on the tuning and based on the environment it's running, we want to give you optimal performance. This is for current storage systems like RAM, disk, flash, and also for new generation systems that are coming up, different kinds of memories that might be there, or any other things where we can store data. I think we need to optimize and get best performance for those. So if you're a vendor who is working on some of those next generation storage software, come talk to us. Similarly, the other point for ours is that we need to be flexible because we want to deploy it on many different environments. This is another reason why I think it makes it easy for a software vendor to reship Facebook inside their code, because we have designed it to be flexible and we want to keep this as part of our core vision. Am I running out of time? Okay. So I have other things, but I think I will probably stop for now and then hand over to Igor is our next?
No, Sage is the next.
Sage is the next one. Okay. Yeah. Maybe I'll answer 1 or 2 questions and then.
Other than the fact that one is not open source and the SQL, do you have anything to say comparing MySQL with this one?
Oh, I think MySQL is an interesting product because they have good benchmark results. And I think it depends again on the benchmark that you're running. So I have not run link bench on it. So this is something that maybe it's worth doing and testing this one for us. There are maybe some other limit, or how should I say it? There are other things in my mind to consider also, like how easy is it to innovate in the code. And personally, I haven't seen the SQL code, so.
But clearly that's not open source, right?
Right. Yeah, I mean, people who have written, right.
Yeah, I said that already. I carefully prefaced me.
Any other questions?
Yeah, so, you mentioned, both on disk and then in memory option. How does it work? Like, if I'm keeping my entire data at memory, like, is persistence disk happening in a background thread, and then what happens if I overflow memory?
I see, yeah, good question. So the question is, how do I keep data persistent if I'm writing only to memory? So what happens is that for the write code path, we write it to memory and we also write it to a transaction log. And then asynchronously we flush these and sort these data in memory and write it to files on the disk and truncate the transaction log. So,
But if it's embedded in your application, I guess.
My question was like, what if I want to really run it as an in-memory database? Like,
okay, got it.
Persistence is sort of like just to recover in case of reboots.
Oh yeah, absolutely. So we do that also. So what happens is that typically you would create a RAMFS file system, which means that your data is in memory. So you can make file mkfs on RAMFS, and then just point RocksDB to the RAMFS file. You could also do other things like keeping big mem tables in memory. But what happens is that when you use RAMFS, the amount of data that you can store in a skip list is far less than the amount of data you can store in RAMFS, because when you store it in RAMFS, they're serialized and compressed or blocks. So you get high storage efficiency. And when you're talking about memory, I think your cost would be the amount of memory that you need. So it probably makes sense for you to use RAMFS and store it that way. So if you store, what about recovery? So if you store data in RAMFS, then recovery is under what you have to do yourself. I think I'll take the last question and then maybe. Oh yeah, so the question is, did you look at Aerospike? So it's not open source. Right, so I looked at what they're doing, but I have not benchmarked or I have not seen the code.
I thought they open sourced it last year.
Oh, they open sourced it now? Okay. Aerospike. I see, okay. So, but when I started this project, that time it was definitely not, because I talked with the CEO at the time. Okay, so some version of it might be open source now. Yeah, okay, last question.
So tell us about the performance numbers, particularly if my application is multi-threaded, the thread within the application can share the data.
Yeah, so I think good question. So one of the design features is to scale linearly, I should not say linearly, scale well with CPUs. So the read code path is very well scalability is very easy for us. Because if you look at RocksDB, the whole database is kind of broken up into one small read-write component and the huge read-only component, right? Only the active mem table is read-write. So it's easy for us to do scalability for reads. For writes, I think we are working on something. So Anthony here is actually did a lot of stuff with transactions and writes. And I think there are many other contributions that are happening, but for writes, I think we still have quite a bit of things to do to make it scalable with CPUs. I think that depends on your machine, but I can point you to our performance benchmark page. You can Google for RocksDB performance. You'll see that first hit. Cool, I won't take more of your time because Sage is waiting, so you can catch me after the event and I can answer some questions.
All right, can everyone hear me? All right. All right, I'm going to share my screen. Okay. All right, we're all set. Yep, all right, can you guys see me? You can see me in here? All right, hello everyone. My name is Weil. I'm the Ceph principal architect. I work at Red Hat now, and I'm going to talk a little bit about a new backend that we wrote for Ceph that uses RocksDB to manage our metadata. So I'm going to give just a really brief Ceph background. I'll talk a little bit about our old backend called FileStore, based on topics and why it sort of failed for us, how our new backend is structured called BlueStore. And then I'll talk a little bit about how we used and modified RocksDB, some features that we added and things that we did to help development, and then wrap up. So just a bit of background, Ceph is an object block and file store system designed to give you a large distributed cluster that gives you highly reliable and available storage system. All components scale horizontally. There's no single points of failure. It's designed to be hardware agnostic and run on commodity hardware. And because it's highly scalable, we need to self-manage whatever possible. And of course, like all good things, it's open source, licensed under the LGPL. So one of the sort of the key design goals with Ceph is to sort of move beyond legacy design patterns. So instead of thinking about things in terms of client server, we think of the client talking to an entire cluster of servers, and we try to avoid sort of old style ad hoc approaches to HA and move to sort of new distributed architectures. So Ceph provides 3 different object APIs, or different APIs. There's object RESTful storage that uses the S3 or SWIFT protocol. There's a block interface that gives you something similar to iSCSI. That's a virtual block device that's used essentially with KVM and OpenStack. And then there's Ceph, which is a full-blown distributed POSIX-based file system. Oh, hold on. I'm supposed to be, yeah, hold on. Sorry. Sorry about that. All right, is that better? Yeah. All right, sorry about that. Okay. Right, so Ceph gives you these 3 APIs, object, block, and file. But the key thing is that all of them are based on a distributed cluster called Rados, which is our internal object store that manages all the data that's stored in the system. It ensures that all objects are stored on multiple hosts and multiple racks. Lets you add new nodes, rebalances data, lets you remove things, deals with failures. All that good stuff is handled by Rados, and all the stuff that's layered on top is much simpler as a result. That Rados cluster is composed of lots of hosts that are built out of OSDs. So in a typical host, you have a whole bunch of disks. On each disk, you'll have a file system, like Butterfs or XFS or X4. And then on top of that is an object storage daemon, the Ceph daemon, that's talking to clients or talking to other OSDs to rebalance your data and move it around. At least this is how we used to do things. In reality, there's a small piece of that OSD that is responsible for storing data on that local file system, on that local disk. The problem is that our current approach using POSIX kind of fails, and there are 2 big reasons why that happens. The first thing is because of the way that Ceph very carefully manages the consistency of data on its disk, it needs transactions. And so all writes, every time it writes something, it's in the form of a transaction. Usually those transactions are pretty simple. We're like writing something to an object, or updating its version attribute, and we're writing to a log. But they can also be arbitrarily complex, and you can't do transactions and give them to a POSIX file system and have it work. We spent a lot of time futzing around with Butterfs, which is sort of transactional internally, with various user-space kernel hooks so that we can plug into this transaction system, but that effort sort of was a dead end and failed for various arcane reasons. So in the end, we just ended up doing write-ahead journals. So we take the entire transaction that we want to do, we append it to a journal. Once it's stable, then we go right back to the file system. That works, but it halves our disk throughput and is slow for, it sort of is not very efficient. So that sucks. The other problem with POSIX is that the way that Ceph distributes our objects, we hash every object, and then we sort of order those and distribute them across the cluster based on that. And we need to be able to enumerate the objects that we're storing in Rados in hash order for prescribing and for recovery and the APIs that we suppose for clients. But if we're storing those objects as POSIX files, the POSIX reader isn't ordered at all. And we have some requirement that we have to be able to split directories when we reshard things as well. So doesn't really help there. We ended up having to do is sort of build these annoying directory hierarchies based on a prefix of the hash. So when the directory gets big, we split it into pieces, and then when we have to enumerate stuff, we just read in the whole directory and sort it in memory and return the result. So that works, but again, it's inefficient, it's slow, it's a lot of complex code that we don't really want to contain. And in the end, we sort of just came to this realization that objects was just not the right fit for the backend. On the other hand, a key value interface like that provided by RocksDB is a great fit because it's ordered keys and values. Our objects are ordered because they construct those keys appropriately. So we went to work writing a fresh new backend for the Ceph OSD called BlueStore, which was based on RocksDB for all the metadata, and we would just write all the content of the objects as files that had sort of bogus names. But the problem we ended up seeing with that approach, sort of incremental steps, is that we were still layering our own metadata management in RocksDB on top of an existing POSIX file system that also has all its metadata journaling to manage its own internal consistency. So XFS and X4 have their journal, and then RocksDB has this write-edit log, which is effectively its journal, so we have this double journaling thing that also was inefficient. So we decided to bite the bullet and basically reclaim the whole stack and write what we call BlueStore, which is effectively NewStore directly over a block device. Why did we choose RocksDB to embed in this approach? We found that it had sort of the ideal key value interface. It gave us transactions, it gave us that ordered enumeration, and it gave us fast commits to logger journals that sort of we could control what was committed and when. It had a pretty standard interface. We could swap in other key value databases if we decided at some point that RocksDB wasn't the right fit, so it was a safe bet. The way that RocksDB is written along with its level DB heritage, it abstracts the storage backend into this environment structure that hides all the details of how it actually stores its data, normally on top of files, and so we could re-implement that and plug in something else underneath, which ended up being very useful. It was C++. But I think one of the key things is that RocksDB has an active and strong open source community, which makes it a safe bet for us to rely on and to invest in, because we know we're not going to get stuck sort of holding the bag if things go wrong and end up relying on it. So the way that BlueStore is put together, we use RocksDB for all of the internal metadata for the data that we're storing, so the names of the objects and all the metadata about where they're stored on disk. We use the write-ahead log, and we effectively do our own write-ahead logging inside RocksDB's write-ahead log, so we just write key value pairs that are short-lived. And we store basically all our other internal metadata, we just cram in RocksDB because it's super convenient interface and very, very flexible. And then when we store the data associated with our objects, we just allocate the blocks and write them directly to the block device. We made all that allocation policies pluggable so we can easily deal with things like SMR drives and those become more prevalent. And the key challenge that we had to do was make it possible for BlueStore, which is sort of directly managing the block device, to share that disk with RocksDB. So we wrote a new RocksDB backend that implemented that abstract interface I mentioned, and wrote sort of a very simple file system called BlueFS that is just complicated enough to store RocksDB data. And that allows us to put all of that on a single device and sort of streamline the whole stack. And the good news is that we sort of implement all this and start testing it, and it's basically twice as fast out of the gate on hard disks and even faster than that on SSDs, which is a huge win by just changing the software stack without having to change hardware and SSD clusters. So we're pretty pleased with that. I'll switch gears a little bit. I'll talk about some of the things we did to RocksDB that made it work better and well for us. The first thing we did was change the way that RocksDB does its journaling. The problem we noticed was that RocksDB is appending things to its log, and that amplifies itself into multiple IOs. So if Ceph does a write, it has to write the actual data somewhere on the disk, and then it has to update the metadata. So there's one IO to write the data. RocksDB does its append to its log file, so that's one IO to write RocksDB's data. And then it does an fsync, which has to update the underlying file system's metadata about that log. So that's at least 3 IOs and sometimes 4, depending on what file system you choose. You just write sort of one IO, which is pretty annoying when you think about IO amplification. There's a capability or feature in RocksDB to use reallocate those files. That limits fragmentation, but doesn't actually help this problem because you still have to tell whether the file is allocated or not. And basically the limitation was that when RocksDB was replaying the logs, previously it would only understand reading all the way to the end of the log file, or reading part of the way through the log file and then seeing zeros for the rest of the time. It wasn't prepared to see a bunch of garbage that it didn't understand and sort of tolerate that situation. So we implemented a new feature called journal recycling. The basic idea is that when we have old log files that we've already written to, we've already rewritten that data to the SST, and we're about to delete them, we instead keep that file around because we know that the disk space is pre-allocated and sort of ready to reuse. And then when we write new log files, we just sort of swap in one of those old files in place and rename it, and we overwrite all that old garbage log data with the new log data. And then later, if we have to replay the log, we just pay attention to our CRCs. So if we see garbage, then we assume that's the end of the log. And even if we happen to see a valid record because we just happen to read the old thing that had a valid CRC, we also look at the log segment generation of the old file, so we know that it's old, we can throw it out. So now we get one log append, and it only results in one IO going straight down to disk. So we sort of got back to the situation that we would have hoped would have been the situation in the first place. So that was great. We pushed this upstream. It works. We use it extensively. There's one bug fix that hasn't been sort of merged upstream yet, but hopefully that'll make it up there soon. So that was great. That really helped with our small IO performance. The other thing is, as I mentioned, we wrote this whole little toy file system that's just complicated enough to store RocksDB files. RocksDB has a very simple way that it interacts with the store system. It just writes sequential files in their entirety and closes them, and never touches them again except to read. So it's very easy to write sort of a very simple and easy to verify file system that would do just enough to run RocksDB. So we did that. We added a few things so that we can map the write-ahead log data, those files, onto different devices. So like the RocksDB log, we can direct at an engineering device. The SSTs, the hot ones, go to an SSD, and the cold set would go to a disk, or whatever. And we made it interact well with BlueStore, so it shares the space. So that was good. Sort of had a nicely integrated platform. We added a tool that that was really useful when we were writing that new backend, that effectively mirrors two different backend implementations. So when you write, it writes to both of them, and when you read, it reads from both and asserts that the result is the same. So this was really valuable when we were developing that BlueFS backend, because we could basically have RocksDB mirror all of this stuff to the legacy default thing that's writing to regular files, and also writing to our backend. And we could tell that our backend was always giving the exact perfect result, and we call all sorts of bugs this way. So that's now in the RocksDB source tree, so other people who are sort of in the same boat can also use that for debugging. That was nice. And then there's sort of one other thing that we want to do that we haven't done yet. There's this one peculiarity of our workload where we have a lot of keys that we write to RocksDB that are short-lived because they're effectively journal entries that we insert into the database sequentially, and then a very short period later we delete them. And because of the way that log compaction currently works, often those get written to the level 0 SST and then get thrown out sometime later, so there's some write application that happens. And our goal is to change the way that log compaction works the first time around, or merging, I guess it's called, so that those short-lived keys never get amplified in the first place. And I think this is not all database workloads see this kind of pattern, but I think a fair number of them do, so I think this is going to be something that's generally useful. But working with some other Ceph contributors to get this work into RocksDB, it'll certainly help our workload quite a bit. And we're excited about contributing more upstream to RocksDB to help make it better for lots of other people. So that's it. I guess in summary, Ceph is great. It's a distributed source system that does object block and file, and you should look at it if you haven't yet. Our sort of previous choice of using POSIX to store files in the backend was a poor choice. I guess it was easy, but it had a huge performance penalty, a lot of complexity we had to do to just make it work. So we wrote a new backend called BlueStore. It's awesome. It's much faster. We embedded RocksDB, and it was very easy to do that, and it worked really well. We're very pleased with that choice. We made a few changes to RocksDB, log recycling, improved our small IO performance, and there are some other changes like delayed merge that we're planning on doing soon as well. So that's it. I'm happy to take any questions. this one.
Sage, let's see if there are a few questions. And I'm going to, if you hear the questions, I'm going to run the mic, but we'll repeat
Okay.
it. Questions
Yeah.
for Sage? Yes. Oh.
Okay.
So how far away for RocksDB to be truly real-time database? And I assume RocksDB is truly highly stable, scalable, highly available. But how we gonna do capacity planning?
So Sage, I don't know if you heard the question.
I heard parts of it, I didn't fully understand. Something about how far away is RocksDB from being a two-way database? That's what it sounded like. That doesn't seem right.
How far away for RocksDB to be true real-time database?
True real-time data. Okay.
So you through relational database?
No, true real-time.
Real-time.
Yeah, in memory, like memory. And the other question, how we can do capacity planning? Because your scale the cluster is many. So how we can do capacity planning?
Okay, so I think there are two questions. One about RocksDB performance and the other about capacity. So I can speak to sort of our requirements. RocksDB is more than fast enough for what we need to do. At least we haven't run into problems yet. We're sort of going through the process of making Ceph work really well on NVMe, and we're looking towards persistent memory hardware that's coming up soon. And so far we haven't run up against issues. I'm sure there's going to be things that we run into that we'll have to work through. But I think one of the reasons why RocksDB is a good choice for us is because that RocksDB community is attacking the same problems, so we're keeping these there. As far as the size of how big the databases get, in our case, we're using RocksDB just to store the metadata for the other data that we're storing. And so generally that's going to be a fraction of the storage device that the OS is managing. So if it's like a 6 terabyte disk, hard disk, then RocksDB portion of that is probably going to be hundreds of gigs. So pretty modest. In certain cases, if Ceph is storing all key value data in those objects, and that gets shuffled in RocksDB, you could conceivably be the whole device. But still, usually just the way that Ceph is deployed, it's a single device. So any individual RocksDB database would be, like some number of terabytes, 6 terabytes, there a couple of years, maybe 10 terabytes. So nothing too huge. And so far, we're not concerned. So.
I have a quick point, not a question really. IBM systems have been doing this circular logging forever, C++ decades, and so that's how we avoid having to reformat and find the end of the log.
Yeah, pretty much every system that has a journal does circular logging. The only reason RocksDB and MongoDB weren't doing it was because their logs were layered on top of files in the file system, and the simplest way to do it was just to append the fresh files, and nobody bothered to go back and make them circular. And so we wouldn't do that. So this isn't certainly a new thing, but it did make a big difference. And I think as this code becomes a little bit more stable and more people start using it, then other RocksDB users will be able to take advantage of it. So that's good news for everyone.
Great. Thank you, Sage. So we'll let you go to sleep. Next we'll have Igor from Facebook talk about MongoDB and RocksDB.
second player is MongoDB. How many of you have heard of MongoDB? It's pretty good, almost as much as you've heard of about RocksDB. So it's, MongoDB is so yeah, MongoDB is a document database. It's very popular, especially around startups. It's been getting a lot of attention lately. We all know, a lot about it, so I won't waste too much time there. And the third actor in the story is Parse. How many of you have heard about Parse? Okay, that's good. So Parse is for those of you who haven't heard about Parse is a mobile backend as a service. So let's say you're a front-end developer, you're building your app. You don't have to touch any of the code on the server. You don't have to deploy anything. You just start writing your mobile app, and Parse handles storing data, indexing data, querying data, everything for you. It's a pretty neat system, and it got acquired by Facebook in 2013, and the usage exploded. At that time, when we started the story around 2014, they were having a lot of scaling issues in MongoDB. Parse was running one of the world's largest installations and deployments of MongoDB ever. So the problems they were facing were unique to them, and it was hard to get some attention, and it was hard to keep scaling up this system. So we decided to help them. The story starts in June of 2014, when on the stage of MongoDB World 2014, this is Elliot, CTO of Mongo. He announced that Mongo decided to implement, let other storage engines implement their APIs. So basically what they decided to do is take their whole storage engine, which they call ML, abstract out the APIs, and let other players in the market implement that API, and then basically you have MongoDB running other storage engines. And on the stage in June 2014, they actually showed the running prototype of integration with RocksDB. They actually chose RocksDB in 2014. And it did some very basic stuff. You could insert the key in there and read it back. Didn't pass all the unit tests, but it was actually nice, nice first implementation. This is all taken from screenshot from the video of the MongoDB keynote in MongoDB World. And I think, opening up your storage engine API was the right choice for MongoDB. At that time, they had a lot of performance issues, and the only way they could solve them was by just changing fundamentally how they think about storage. And then from June 2014 and onwards, they kept working on MongoDB RocksDB integration. We were very excited. MongoDB is going to adopt RocksDB, will be deployed to many more servers in coming years. But then in October 2014, they called us and said, hey, we decided not to actually go with RocksDB. This is sad cheetah. We were sad at the time. We were excited, but it ended up not happening. And it made sense, right? What they said is, we can't adopt RocksDB because if they take MongoDB and deploy it to Goldman Sachs, and there's a bot in Goldman Sachs called at 2 a.m., and they call MongoDB, and MongoDB says, oh yeah, that's a bug in RocksDB, but we can't call Facebook. They will not, they will not answer their phones at 2 a.m. So okay, that makes sense, right? They want to control their stack, although they are still working on the pluggable storage engine. So the question is, who's going to replace that storage engine that they don't want to use RocksDB? So what they did in December 2014, they decided to acquire Wiretap. Unfortunately, they couldn't acquire Facebook, Wiretap was a small startup, actually very good storage engine built by people with tremendous experience in database and storage engines. One of them, Keith Bostic, worked on BerkeleyDB like long ago when I was in like middle school or something. BerkeleyDB, yeah.
What's his name?
Excuse me?
What's his name?
Keith Bostic. So now he works for MongoDB. They acquired Wiretap, and that was definitely the right choice. Wiretap is a great storage engine. They integrated closer together, and they shipped the product. However, we decided to take on the project. We didn't want MongoDB plus RocksDB to die, so we just decided, okay, we'll focus our full strength on it and make it a reality. The reason here is that basically Parse, the way they use MongoDB is very atypical. So what they do is they multiplex many different
cluster. So you have one MongoDB instance running with, let's say, 10,000 or even 100,000 apps on one MongoDB instance. And then each app has 10 or 20 or 100 MongoDB collections. Collection is basically something like a table in MySQL. What that means is their first version of MongoDB Wiretagger had one file per collection. And if you have 100,000 apps, each app has 10 to 100 collections, that means billions of collections, which means millions of files. So we knew that if MongoDB continues working with Wiretagger, parse would never adopt it. So we will be missing out on a huge advantage here that Wiretagger brings. So we decided to instead keep working on our own and make it so that our solution works well for parse. Works well for situations where you have a lot of different collections.
Did this still have the database level logging?
Correct, yeah. Both Wiretagger and RocksDB have all that. So we took it over, we worked on it. We had some very interesting projects of making sure everything works, all the unit tests pass, concurrency works properly. We also had this thing called Flashback. Flashback is a system that will let us record live traffic that's happening to MongoDB instance, and then later in the offline mode, we play the traffic back to the cluster. And that way we could start two MongoDB instances, one with old storage engine, one with RocksDB, and just measure performance. And so while we were doing this, still, database wasn't kind of like stable mode. I mean, we started working in October, and this was March 2015, so maybe 5 months passed while we were like making it, making sure everything works. But then there was this app on parse that just started getting viral. Like, just a lot of people were using it around the world, and the old MongoDB that parse was running just couldn't handle it. So we had two choices to make. One choice was we could just, tell their app, sorry, you're going to fail. We'll just throttle you, or you can't run parse anymore because your customers, there's too many customers concurrently, and you just can't handle your workload. So that's a sad story, right? If you have a viral app, you can be like a billionaire, but you will not be because parse, had very bad experience. So instead, what we decided to do is just roll out MongoRocks. We started MongoRocks on one replica set that handled that viral app, and here's what happened. So these are the latencies. This is the actual graph. Latencies are in hundreds of milliseconds on the y-axis, and you can probably guess where we deployed MongoRocks. So the latencies went up to like 600 milliseconds on average. So average customer of that app had 600 millisecond latencies, and as soon as we deployed MongoRocks, everything went better. And this gave us some, confidence of deploying it everywhere else. And since March, we started deploying more and more systems that parse had. In September 2015, we also received some external recognition. Percona announced they will offer enterprise support for not only MongoRocks, but also pure RocksDB. And we are very grateful for them to do that. By that point, we already had many releases of MongoRocks, stable releases. We had external customers as well. And in October 2015, we actually finished out the rollout. So parse was fully rolled out and using mostly MongoRocks, no longer old storage engine. And what this gave us huge storage savings. As Juba said, first test was like we loaded 5 terabyte replica set into 285 gigabytes. So we got 90-95% storage savings. We see much faster writes, I think even 50 times more than 399 because of document level locking. And for reads, it was kind of like on par. The slide, it's on the web, so you can just Google RocksDB support. Yeah, it's already here.
So on the earlier slide in the graph, what was the storage engine used there before?
So this was MongoDB 2.6.
The MMAP one?
MMAP, yes. Okay. And only one storage engine.
Okay.
Yes. So yeah, we rolled it out fully on parse. Parse was very happy. We have been, rolling out fixes everywhere, and yeah, this is a happy story. So let me now go back to an earlier point I made of multiplexing more collections on a single namespace. That was very important because of the way parse handled the database. That was the main reason why parse couldn't just use MongoDB with WireTiger. So the way we store a single collection in RocksDB single namespace is by adding 4-byte prefix to every key. So there are three kind of like concepts in MongoDB that we have to map to RocksDB. A collection, which is just a table, a collection of JSON documents, unique index, and a secondary index, or non-unique index. So in collection, the way we represent keys and values in a collection, in a MongoDB collection in RocksDB are by 4-byte prefix and an 8-byte record ID, and those two map to a JSON document, just binary JSON document. Unique index, we have a 4-byte prefix and the index key, and that maps to record ID. So when you search on a primary key or unique index, you find your record ID, and then from record ID you get your JSON document. And then for non-unique index, the difference is that for a certain index key, we can have multiple record IDs. So we put record ID in a key. That way we can have multiple record IDs for one index key. The biggest challenge is most of stuff actually mapped really well. Like, as people said before, RocksDB API is pretty simple. MongoDB's API was mostly pretty simple, but there were some rough spots that were kind of like challenges of integrating MongoDB and RocksDB. And the biggest one was transaction support. When we started rolling it, like building this solution, of course MongoDB didn't add any transaction support. They were pressing basic unit tests, but as soon as they went multi-threaded, they just said, we'll fix it later. And at that time, we didn't have RocksDB support, which we do have now with Anthony built in version 4.0. So instead, we had to roll our own. And the way we do it is just keep a list of keys that are currently being written to. And all the open transactions are written right into a set of keys. We keep that in a hash table. And then every single time the transaction wants to write to a certain key, it has to first check that hash table. So we built this in the layer, in the MongoRocks layer. The second challenge was around performance. So MongoDB has this thing called oplog. Who holds oplog as a part of the storage engine. Oplog is something like MySQL's binlog or replication log. When you write a certain key and value in MongoDB, it goes to the collection or to the index, and it also goes to the oplog. And that way, when you have a secondary coming into the replica set, it just tails that oplog to get back to its updates. The problem with the oplog and the oplog cleaning is, let's say you have 10 megabytes per second coming into your oplog. An oplog is a circular buffer. What that means is you also have to delete 10 megabytes per second from your data, from your beginning of the oplog. The beginning of the oplog is usually cold. Nobody is reading it. Your secondaries are telling the tail, but head, the one that we have to clean up, is cold. So basically, 10 megabytes per second write would mean 10 megabytes per second read for the delete. We did some clever optimizations there, so we don't have to read when you delete. So when you write 10 megabytes per second, you don't actually have to delete 10 megabytes. You have to read 10 megabytes per second from the head to delete it. And that gave us a lot of performance wins when oplog gets stable. And then one other interesting challenge we had is how do we delete the collection? With WireTiger, if you have a file per collection, you just delete the file. That's easy. If you don't have a file per collection, you have a 4-byte prefix, then what you could do is you can just get all the keys with a certain prefix and then issue deletions. That's not, that's possible, you can do that, but it's not very performant. Then what we do is RocksDB has a process called compaction, as Ruva described. So you get two files merged together and write a new file. And we also have a concept called compaction filter. And that's a callback that we call for each key that we pass through compaction, and the callback can decide whether or not we should keep that key in the database. So basically, when you delete the compaction, you just say this prefix is now deleted, and then during the compaction process, we just filter out those keys for the deleted collection. So we don't reclaim the space immediately, but as compaction is happening, you get your space back. And then, kind of like high-level comparison is other storage engines. When you compare both WireTiger and RocksDB against mmap, both of the storage engines offer great compression. RocksDB is slightly better than WireTiger, but in the grand, I think we are better maybe like 20-30% depending on data set. But when you compare two of us, WireTiger and RocksDB with mmap, you'll see 10x storage savings in almost all cases. your data fits in memory and you don't write that much, if your write is like less than 1% and you are mostly read heavy, then we found that mmap actually works quite well. As soon as you start writing, then your concurrency hurts because you can't read and write at the same time. And then both WireTiger and RocksDB, which have that document locking, start getting faster. Between WireTiger and RocksDB, if you have millions of collections, WireTiger currently can't do that. And this is a parse case, so we are a clear winner there. And for other stuff, our benchmarks show that WireTiger is slightly faster on inserts, like less latency, more throughput. And RocksDB is better in storage efficiency, so it reads less per query, and storage savings are a bit higher than required. So that's just high level, but if you are running MongoDB and you're trying out storage engines, it makes sense, try it out. It's easy. You can even have a replica set with one node running RocksDB, another node running WireTiger, so it's very easy to compare. And this is what we, if you're running MongoDB, just try it out and see what happens. So what's the future of MongoDB project? There was news last week that parse is shutting down, which means we will likely not run MongoRocks in production at Facebook anymore. However, I'm still optimistic about MongoRocks project. MongoDB keeps getting better. I'm very bullish on them. They are doing some very interesting stuff. They're moving faster than any other database out there. RocksDB, of course, keeps getting better. We have very ambitious plans for RocksDB. The people in the room here are evidence of that. This is actually a graph of the RocksDB commits. There's a big dip in doing a lot of stuff in one heat, but you see that the number of lines of codes are linear, so we are definitely investing a lot of resources into this, and not only Facebook as a company, but also other players in the open source community like Sage and other people. And then,
What's the color coding?
I think this, the languages, this is C++, one, I don't know what it was. I think green is Java. And then the MongoRocks layer is actually pretty thin. We still have some transaction support, but we're also replacing that with RocksDB's native transaction support now that we have it. So currently it's only 6K lines of code, we'll go even lower. So we hope that with the power of open source community, we can keep this project alive. People will keep running it, Rakuten supports it, and we'll get a lot of contributions. And with both the upper layer, Mongo and RocksDB getting better, this project is getting better. Hopefully in the future. Cool. Thank you very much.
So parse is getting replaced with something?
Parse shut it down. That news just came out last week.
So that's the open source implementation that you guys are facing with parse from MongoRocks.
MongoRocks is open source.
No, not like the particular thing that I saw that parse was released as
I mean, parse was released as open source. Parse server was released as open source. But basically, parse server connects to any MongoDB instance.
Oh, okay.
So the storage engine doesn't matter. You can still have the same MongoDB API. MongoRocks was started as open source project.
You mentioned a couple of things. One was performance, and second was efficiency. First question on performance. They comment that RocksDB is targeted for both memories and the newer kind of flashes which are coming up. What kind of software protocol stack it uses to talk to these memories? To take advantage of the faster memories which are coming currently and going forward. And second, on the efficiency, why does RocksDB get better efficiency compared to other key value systems which you're comparing with, right?
Okay.
What makes it?
Okay, both of those are good questions. First question is, what protocols are we using to talk to new current and new storage media? Memory, flash, and other storage media coming. Currently, all that we do is block device APIs or file system APIs. That's the two things that we are currently talking in terms of protocols. So even with if you run on memory, and we currently have some usages of not MongoRocks, but RocksDB running on memory at Facebook. And what we do is we mount log device as RAMFS, so dev as SAGM, and then we just run RocksDB normal file system. And that is it. The second question is, why is efficiency better? And Single actually has very detailed talk on MySQL, MongoDB versus RocksDB, which will basically explain the differences why LSM engines have better storage efficiency than B-tree engines. And so he'll go very deeply into this discussion, and hopefully he will also answer your question. If he doesn't, then find us later.
You did not answer the protocol stack for the newer release.
We don't know that yet. So new members are coming. Our vision and what we plan to do is support them, but maybe not only us, maybe open source community, maybe vendors of those storage engine devices, storage devices. So we don't know yet what we use, but currently what we use is block device. We can also have Q&A session later. Let's get rolling, and then we can take questions. Yeah, we will have Q&A session with all the speakers there. Yeah.
So next we'd like to have, we'll change kind of direction a little bit and have Qian Zhu from Rakuten Marketing, I think, speak about her use of RocksDB.
Good evening, everyone. My name is Qian Zhu. I'm from Rakuten. So today I will be talking about the use case of RocksDB in our real-time reader. A little bit about myself. I joined Rakuten last September, so it hasn't been half a year yet. But it's a very good company, very challenging problems to work with. Before Rakuten, I worked at Accenture Technology Labs for a little bit over 4 years. Over there, I was a research manager, so we worked on different sorts of problems, focusing on the infrastructure system, but we started from cloud computing infrastructure all the way to IoT. So I gained a lot of experience with new technologies, but I kind of have the feeling I don't have the depth into one of those technologies. So that's why I left Accenture and joined Rakuten. So for myself, I graduated from the Ohio State University in 2010 with a major in computer science and engineering. So in our PhD program, we have one major and two minors. So my major was in distributed systems, but I also have a lot of interest in machine learning and data mining. So basically, a lot of system problems, we do have a lot of data, and in order to study and get insights from the data, you need data mining and machine learning techniques. So how many of you have heard about Rakuten or have used Rakuten before? Okay, probably not even half of it. So Rakuten actually is third largest e-commerce retailer all over the world. So we all know about the first two, right? Amazon and Alibaba. Okay. So Rakuten is the largest, it's a Japanese company, and it's the largest online retailer service company in Japan. And specifically, I want to talk about Rakuten affiliate network. So in the advertising business for affiliate network, you want to connect affiliates or the publishers with the advertisers. So for the publishers, you want to put ads on your webpage so people can click on that, and then there they might convert to purchase. And for advertisers, you want to advertise your products, right? So for Rakuten Affiliate Network, we have thousands of advertisers to partner with, and we're driving billions of dollars of revenue every year for the advertisers. So the challenge we are facing here is that, first of all, it's low latency. And in order to respond to a big request, so when a user visits a web page and you have this space to display your ad, a lot of advertisers will try to put in their bids. So they will try to say whether I want to make a bid and how much I want to put in it, and the winner of the advertisers will eventually put on their ad in there to display to the user. So in order to do that, you have to respond to the bid requests in tens of milliseconds. That's the first thing. And the second thing is that we have a lot of intensive random query, and those are single queries into the database locally. And for each of the bidders, we hope to handle up to 100,000 QPS, and we have tens of bidders across the whole world. So for our bidders, each of the bidders will reside on a server. And for our RTB, actually we have implemented our RTB using C++. And we want the database to be embedded in our software. So when we deploy the bidders, it will be easy to deploy, right? So, and every time if a bidder goes down, and it will be easy to resume or restart from where we left off. And you can have the database files from other bidders to start with, and then try to load data from message broker, for example. Yeah.
Up to 100,000 queries.
Yeah.
What's it? I mean, latency, right? Because it's just throughput, right? So when query finish, another starts, so we maintain the throughput. But with other performance estimates from the legal to the
Right now it's just latency. It's just latency, so we have to respond really quickly in milliseconds. Another requirement or challenges we're having is that the parallelism, right? So we will try to load data into the database while we try to handle all the queries the random queries to the database. And as each of the data will have a TTL, we have to make sure that the expired data gets deleted from the database as well as from our bidder, so that it won't get its outdated data. So here is our architecture design. All the data flows into Kafka, which is our message broker. And the data flows into all kinds of topics. So for one of the path is from Kafka to RocksDB, which is the right thread. So in the right thread, all it does is that to fetch messages from Kafka from each of the topics, and then just write to RocksDB. Another path is that we will have queries from bidder. So if a bid request comes and they try to look for the data in the bidder, so that if it gets lucky, so if we have the data in the cache, in the bidder cache, then we will respond immediately. But a lot of times, or even 80 or 90% of the times, it's a miss, which means that the bidder will issue a query into the database and try to look for the data. And in another case where the database, even the database doesn't have the data, then we will throw into a negative cache, meaning that we will try to get the data from our global data store. So RocksDB serves us as our embedded database in here, and the whole package is that as I was mentioned, data was written implemented in C++. And in our RocksDB library, we have a RocksDB library written in Rust. So just FYI, we serves as a database on a single server.
And it's never put into the global.
It will send it, yeah, okay.
Oh.
And what are you using to populate the database?
What?
What are you using to, how the data comes to the database?
From all these RocksDB.
No, it doesn't show from us, it shows the other way around.
No, we didn't show the path where the data synced from RocksDB to the global store. This is more for a bidder to show that what if the bidder cannot handle the data, then it goes to RocksDB.
So what are the other parts of your real-time data pipeline, your technology stack, data ingestion part, machine learning part? Can you describe that a little bit?
So just briefly to talk about that, we have our pacing server, which make a decision on all the bidders. If I'm a bidder, I have a budget, right? So I want to make a decision whether I want to display the ad or not.
I'm talking about not your internal, open source, like front end, you might use a Kafka or whatever, use Spark, any open source solution. I'm not interested in your internal solution. You don't know what kind of internal solution.
So all the data will flow through Kafka.
Okay.
And the Kafka will go through the Rust process we have, it will go to RocksDB. So that's the path.
How about the engine? Your analytics engine. You have you have a sort of retargeting engine, right? That's your own.
So for our, talking about analytics engine, right?
Yeah.
So the analytics engine were written is by another team in our company, and it's right now we're just using open source libraries from Python to do that.
When you go to start from the new ones here, the Kafka, which I was telling you about last, right, you told me that Kafka.
I guess this is where experiencing, trying to experimenting with all sorts of open source. So as I was saying, the RocksDB use case in our case is that we have write-thread, which just to read it from Kafka and write into RocksDB, and we create multiple column families for the data we have to do. And one of the features we really like from RocksDB is that they have the prefix seek, which means because our key is a combination of two parts. So for a specific ID, XID, so if it's IP data for specific IP, because it's associated with multiple segments. So with that feature, we can fetch all the data related to that specific IP. And also we have the queries thread. It have the take advantages of the range scan as well as the random single record retrieval. And we have the expiry thread. I know RocksDB has management of TTL, and we're not using it right now because we want the expire frequency to be customized. So at a certain time, we want to trigger the thread and expire data at that time. So moving forward, there are a lot of performance tuning we want to do from the first release of our new generation of our RTB. We embedded on RocksDB, and we were actually together with another project from Facebook, we were able to demo our QPS. So from the next generation release we're working on, we want to look into more performance tuning of RocksDB, because eventually we want to hit 1 million QPS for our RTB to handle. And we want to also apply RocksDB to other Rakuten services. So we want to accompany all to try out RocksDB, because our experience with RocksDB is really good. And lastly, we are hiring, so we want engineers and we want machine learning experts to come and join our team. Thank you.
Thank you. She'll be announcing you. She can ask a question. So finally, we have Seeing Dawn from Facebook, who's going to talk about MySQL on top of RocksDB.
hello everyone. My name is Lee. I'm a software engineer at database engineering team at Facebook. I'm here to introduce MyRocks, which stands for RocksDB storage engine of MySQL. So the first question some people asked before, so why we need to get another? So why we need to get another storage engine for MyRocks? Is the current ones not good enough for us? So here's the answer. We start with this basic architecture of Facebook. As we know, Facebook has a three-tier architecture: stateless front-end tier, and memory, mostly memory tier, caching tier, and persistent tier on MySQL database. So we are trying to optimize this MySQL tier in this project. So this is a tier of SSD devices of tens of petabytes of data. So before optimizing it, we need first to understand the metrics of it. What's the bottleneck in it? What's the statistics of this hardware metrics? How it looks like. So here's how it looks like. So we can see both the read and write IOPS are far lower than what the device can provide. Also the peak write bandwidth and CPU are pretty low, and as the write endurance is good enough for us to keep at least 3 years or longer. So what's the bottleneck? The bottleneck is going to be the space. So if we can store more data into this device, we have no problem to serve the read and write output. So the problem is how we can store more data into the same device. So that's why we have this RocksDB storage engine, or MyRocks. So this project started with open source project. You can also go to our GitHub page, download code, build it, and try it out. So how RocksDB compare with InnoDB? So in terms of space and write, well, Zhuba already showed this graph. We run the social graph data and show that RocksDB's size on device is less than half of InnoDB's. At the same time, we write less than half of the data to the device as InnoDB. So which means we can store double the twice of the data in the same device as what we're storing in InnoDB now, which is very good. Why is the case? Next question, why? So we come with the space application first. So InnoDB store data in B-tree. So in B-tree, the space wasted mostly comes from the fragmentation. It comes from the fragmentation of the B-tree. For example, if the database page is 16 kilobytes, in a lot of pages, they're not full. Likely we are wasted some data in the page. Furthermore, when we compress the data, let's say we compress the 16 kilobytes of page, we compress to 5 kilobytes. And in InnoDB, we cannot just write 5 kilobytes for the data. We have to find 8 kilobytes line area, and just to write down this 5 kilobytes bytes. So in this case, we again wasted 3 kilobytes of data because we have to write a line page. So in the worst case like that, we can waste up to half of the space. On the other hand, for the RocksDB, the space application mostly comes from the stale data we updated but didn't clean up. So because we write the data without alignment, so everything is like there's no space in the middle. But there are some data we deleted or updated, but they're still in the LSM tree and we didn't remove. So to the estimation of those pieces of data that we still in LSM tree, the estimation will be less than the total data other than the last sorted one or level in in this graph. So it will be less than 10% of data. So that's much better than some of the worst case of InnoDB, which is up to half. So this is good for the space application. So why it is also good for write application? So in the worst case, because it's an in-place update solution in InnoDB, when we update the role, we read a whole page to memory from the device. Update a single role, and if we're unlucky, we have to write it back to disk. That means the write application will be the page size divided by the row size, because we only update one row and we write back the whole page. So with a page size of 16 kilobytes or something, the write application can be easily as high as 100 or more if the record is not big. So on the other hand, the RocksDB's write application comes from how much time we rewrite the data for the single compaction. For in this example, we have each level of the data 10 times larger than the previous one. That means we will rewrite 10 times more data when we compact data for the next level. So if we have 4 levels in this case, the write application will be 10 for each level, will be 40. So 40 sounds like high as a system, but actually it can be much lower than the B-tree solution like InnoDB. So that's why RocksDB is good in terms of write applications. Question?
I just want to make a quick comment. For any MySQL storage, if you can use or build a custom memory manager, this is not a lot much. So kind of problem can be gone immediately. So actually, I have a question: is what kind of storage architecture do you have in your RocksDB custom? Like it's like Ceph or DAS, direct attention storage. What kind of hardware storage architecture?
So the question is, what kind of hardware storage we're using?
The storage like command machine with direct attached disk, right? Or traditional Ceph, which NetApp or VMware that we.
Yeah. So the question is whether we are using something like SAN or we're commodity. We are actually using the commodity host. We are mostly like PCIe flash card and mounted as a disk. So that's mainly what we use.
Does the RocksDB support full in-memory processing? Full in-memory?
The question is, does RocksDB support full in memory? Like Juba already mentioned, we store persistent data in file system. So technically, you could create a runfs and store the data.
Yeah.
Well, definitely this is
for persistent.
Yeah. So the persistency is not guaranteed by this solution, but there is a workaround using our backup engine that we can periodically back up our data to a remote persistency service, let's say HDFS or hard drive. Definitely, you might lose some data between backup. You may make it run from by something like storing the transaction log in hard drive or something. Yes, there is a workaround, but it's not like very native support. I think hopefully that answered the question. Yeah. So the conclusion is for the B-tree solution, the worst case right now suffer and RocksDB is better. So let's go back to how about core ecosystem performance. Where we optimize the space and write is query QB has become worse. So we run this big batch, which is the benchmark we care about most. And in this benchmark, actually, RocksDB has a better query per second than InnoDB. And also, it has a good better read amplification than InnoDB. So it's read from device less time than InnoDB per query. But definitely it's only one of the benchmarks. Although it's the most important for us, we also run several other benchmarks. So most of the benchmarks that RocksDB performance is like comparable to InnoDB or higher. So that means we actually, by some good tuning, we are not sacrifice the query QPS by winning in this space and flight organization. So in order to support this giant, this MyRocks situations, we introduced several new RocksDB features. Here are some of the examples. First is transaction. So RocksDB had before that, RocksDB has two ways of providing consistency. One is atomic multi-write, and another is this special operation called merge operator. So it's end up with is not sufficient for this sophisticated database system like MyRocks. So we built a transaction. That was after Igor built this concurrency control for MongoRocks, which is Anthony mostly built this feature. Anthony. So if you have any question about this cool features, just ask Anthony. So we have two modes of transactions. One is optimistic concurrency control, and one is pessimistic concurrency control. So we end up with using pessimistic concurrency control because of this logging feature of the MyRocks. And we also introduced an interesting feature called single delete. This is because the RocksDB's API supports blank put. So you can put a key, overwrite the same key by issuing another put, and then delete it. Right? So that means when you have a deleted entry, it writes tombstone to the LSM tree. So when this delete marker or tombstone during the compaction meets this put entry, we can remove the put entry because it's deleted. But we still cannot remove the tombstone because there could be a put before this put. This delete still needs to be invalidate. So in that case, we will keep this tombstone for a longer period of time until it's compact to the last level. So the result will be there will be a lot of more tombstone in the LSM tree, and performance will be not that good. So, but actually, the way we implemented this MySQL MyRocks separate index is like every key is insert only and never update and will be deleted. So to make use to take advantage of this pattern, we have this special delete called single delete. So by issuing a single delete, the user promised there was only one put before that. So that when doing the compaction, the single delete marker meets this put record, we can drop both. So in that way, we can drop tombstone much faster than previously and improve the secondary index performance much more. So the third optimization is delete files in range. So this is one running a SQL database. Sometimes people will drop a table. So people want to see the table dropped immediately or quickly, not like waiting for days. So one way to drop data in the LSM tree is to wait for the compaction to happen to naturally drop the data, which will take time, and there's no time bound. But actually in MyRocks we included it in the same way as MongoRocks, which Igor introduced, which we put the table ID as a prefix, so the data for the same table is sit together in LSM tree. So in this example, there's key value for table A, for B, and C.
A tough question for you. So time or timing is very important in transactional database. Suppose your RocksDB cluster fails on NTP, which is timing synchronization. How do you
improvement, but actually we're talking about all the single node database. We're not talking about the distributed transaction at all. So, but that's a good question. If we come to that part, we need to answer the question. Yeah. So, okay. In this example, if we want to drop table B, we can find all the files only contains data B, table B, and just directly drop. And we will still leave some boundary data for the files, but most of the data, if table B is large, most of it are already dropped. So you will see your space drop significantly immediately. So this simple optimization makes this drop table much quicker to reclaim some space, and or definitely later we will gradually remove these data, other boundary data through compaction, which doesn't matter so much. So these are examples of the improvements we did for RocksDB in order to support MySQL. But even if we do that, we need to work around something from in the MyRocks side based on the characteristics of RocksDB. So first example is the reverse column order. So because in RocksDB we encode data using delta encoding, so the forward iterator actually is much faster than the reverse one. So that means if you have a table, your query of order by ascending will be much faster than order by descending, well, which is not good. But we provide a new feature called, we provide a feature to allow user to reverse the column order. So if you have a column and the most common query is order by descending, you can say revert order of the column. And then the most common query will be faster. The other way will be slightly slower, but you optimize for the more common query. So we also built this optimizer stats database. We have to have stats with optimizer, and this is built using the mechanism we have to, when you do the flash and compaction, generate files, we can call back to you, and MyRocks collect stats and store it in the metadata of the files, other storage. So that's accumulated stats. So, are there any limitation of the MyRocks right now? Yes, we have some. We are not yet supporting online PL, not support foreign keys, matrix index, full text, and we are planning to add them in the future. And MySQL InnoDB supports next key locking, what we call gap lock, which is interesting locking. RocksDB is still not supported. So RocksDB's consistent the locking model will be similar to what is happening in PostgreSQL or maybe Oracle data. So that's something to keep in mind. It's not totally compatible, but we're not like implementing something weird thing or lacking feature. We're just doing not us. InnoDB does. So currently we only support replication using rule-based binding logging, and the state-based logging is not yet supported. So that also means your XA transaction cannot be durable. We plan to add a new feature in RocksDB called two-phase commit, and plan to use the new feature to support statement-based transaction log for replication. And also the same question, order by ascending and descending, only one of them can be fast. So we plan to improve RocksDB reverse iterating speed a little bit and see whether we can narrow the gap over time. So the final takeaway, we built RocksDB because of the much better space and right application. And it is end up with comparable performance too. And we built several features to support this MySQL, including transactions with single delete and delete files in range. And MyRocks do have some limitations for now, and we are addressing them in the future. Thank you.
In the interest of time, I will take any kind of questions. questions. I hope some of the speakers will stay here so we can take questions offline.
Questions offline.
And so I want to thank Dhruva, Sage, who stayed up late, Igor, Qian, singing for this awesome evening. And hope some of you will stay back and catch the speakers. Thank you.